So I'm going to talk to you a little bit today about brain-computer interfaces. But just in case anyone's not familiar with them, I'm going to give you a quick crash course on neuroscience that'll help you understand everything that you need to understand about the technology that we build. So you have in your brain specialized cells called neurons. There are 85 billion of them in your brain. It helps you process information. You also have neurons in your skin, in your eye, in your ear. And everything that you experience in the world comes from the neurons in your senses, in your touch, in your hearing, in your sight, receiving information about the world and transmitting it to your brain in the form of neural activity. Every decision that you make, the substrate for decision-making, cognition, are neurons in your brain processing through neural activity. And actually, everything that we do, we accomplish through our muscles. And our muscles know to contract when neurons stimulate them through neural activity. So in some sense, the entirety of human existence as we experience it is neural activity. Now, I want to talk a little bit about...
Sorry, I want to just check that online audience. Can you guys hear Matt's voice well in real time? If yes, can you give me a shout out?
Oh, good, we got a thumbs up.
Okay, we got a thumbs up.
Excellent.
Okay, great.
So now I want to talk about something that I want to pick up on a theme that we had earlier about physical AI. And we talked about AI and large language models. And we asked about, who is experienced with them and how is it affecting you? And almost everyone raised their hand. Everyone's using AI right now. But we talked about physical AI, and not as many people are being affected by physical AI right now. And actually, in a lot of places, we have, for instance, video cameras that are higher resolution than the human eye. We have AI in the loop audio processing that can cancel sound dynamically in your headphones, or microphones that can pick up a conversation and suppress all the sort of non-speech noise. But we don't, if someone goes blind, we can't use any of that technology right now to give them their vision back. Or if someone is deaf, we can't give them the best possible hearing prosthetic. If someone's paralyzed, we can't give them the ability to move around freely in the universe, even though now we have companies like Figure and Tesla building humanoid robotics that are incredible. You see breakdancing robots. And so there's this disconnect between all of these technical capabilities we have in the physical layer, and then these powerful AI tools that we have, and then the human needs that have been with us for thousands of years. And that's the same kind of bridge where we're not able to use the technologies we have to attack some of the most important problems that we have. And that's really the backdrop now for why brain-computer interfaces are so important. Because I just told you that everything that we do is it's neural activity. And we can read and write neural activity using electrodes, using brain-computer interfaces. And so if we can build better brain-computer interfaces, ways of getting into the sensory areas and putting information into our brains, we can connect to these high-resolution cameras that already exist. We can connect AI-enabled microphones to not only give people their hearing back, but also allow them to speak any language using just a little bit of latency and processing. And we can use devices in the motor area of the brain to allow people who are paralyzed and can't speak anymore, can't move anymore, to have conversations with their loved ones and control advanced robotics. But the key is being able to get data in and out.
That's right.
And
Matt, really quick, I just want to make sure everybody, I'm going to pass this around. This is one of the brain-computer interfaces right here. I'll start right there. What you'll see on here is actually there's 421 microelectrodes under a piece of plastic there. So normally that plastic cap will be off of it during the actual surgery. But that is what it goes in through a craniotomy. We put that through the dura of the brain. And the silicon lead here comes down, and the battery's actually in the pacemaker. So pass that around, Matt.
We're building the modems of the sort of new physical AI that is able to connect brains and computers directly. And we're, right now, as I'll tell you a little bit later, we have the highest data rate modems for the brain in the world. The device that Justin passed around right now is the tip of the iceberg for brain-computer interface technology. And so, I don't know, Justin, some of these are your slides. I don't know if you want to chat a little bit.
Yeah, no, when you're thinking about brain-computer interface, there's our North Star. I look at businesses in terms of what are we going for? as Brian was saying, we're going for missions that never expire. In our case, we think there's two keys to the future of BCI. One is durability of a device. We want to give people the ability to get an implant one time, and that device will last for the rest of their lives, which is very different than what Elon is developing with Neuralink, where they've developed a much cheaper material that actually degrades over a 2 to 3 year period, because he believes in a future, maybe 40, 50 years down the road, where we have to get brain surgeries every 4 to 5 years to get hardware upgrades, the same way you would get a new iPhone. So durability is really, really key, okay? The other thing is on data rates. So if you think about why people would get BCIs into the future, what we're essentially doing is integrating AI compute in humans. And in order for us to do really, really complex things, we need to be able to read millions of neurons. And the only way to read millions of neurons is to get more and more electrodes in denser and denser areas of a wafer so that we can cover more neural clusters of the brain. And so similar to kind of semiconductor fabs, like what you're trying to build for is a platform that can scale architecture over time, which is what Paradromics here has done. And they're going head to head with Elon to basically figure out, do we have an architecture that can scale electrode count better so that ultimately we can go from doing things like restoring speech in ALS and paraplegics all the way to restoring vision or even augmenting vision.
The challenge, the advancements that are happening right now in brain-computer interface, they're partly technological and they're partly paradigmatic. So one of the big technological things that's happening right now is a recognition that moving to more and more electrodes means higher bandwidth. And then this sort of paradigm that's happened is realizing that fundamentally most issues with the brain, whether you're trying to understand mental illness or trying to give mobility back to paralyzed people, or you're trying to connect people directly with artificial intelligence to achieve next level cognition, it in the end comes down to bandwidth. It's a data question. And so what I find fascinating about brain-computer interfaces is that we're a therapeutic company. Most people at the company, they get up every morning thinking about how are we going to give function back to people who have lost it. But the technologies and the capabilities that we're building today for therapies, they're immediately, in some sense, they're dual-use technologies because they're also the ultimate enhancement technologies. A visual interface for someone who's blind is the ultimate AR/VR pass-through system. A device that we provide to someone who's deaf to help them hear immediately becomes the ultimate translation system. The device, even in our first clinical trial that we're enrolling for right now, we have people who are in a wheelchair, they can't move, they can't speak, and they're attempting to speak and they're communicating with people through AI, through computers. But that means not only can they have conversations with their family members, but they have a link that's more intimate than we do to AI agents. They can spin up AI agents and they can do workflows directly from their brain that we can't. And so you can see immediately these technologies are not only restorative, but they're enhancements. And so what we have now is we have this advancement of technology where the capabilities are getting better and better, and as more and more people get them, both the safety and the perceived safety of these devices gets lower, so that the benefit-risk trade-off for these devices will eventually pass a threshold where even people who don't have disabilities will be interested in using the devices. And so what we have here is just a little bit of a map of the brain to help you understand the same device that we were passing around can do different things depending on where you put it. If you put it in an area called hand knob that controls the motor output to the hand, suddenly you have a cursor, you have typing, you have upper arm robotic control. If you take that device and put it in an area called 6V that controls the mouth, the tongue, and the larynx, you can read out what people are intending to say and do speech directly through a computer. But you can also put a device in visual cortex, and if instead of reading signals, you put signals into the brain, you can create pictures. If you put it in auditory cortex, you can either hear what someone is hearing or cause someone to hear something that their ear either can't or wouldn't have enabled. And so just moving this device around creates opportunities.
Yeah, the one thing I want to add on this is for a lot of you that have invested before, obviously when you look at investor decks, you kind of see total addressable market, giant circle, billions of dollars, and then maybe a subset of that you would actually address. The The exciting thing about BCI is these are trillion-dollar markets. Okay? Right now, our FDA clinical trials, both for us and Neuralink, we have the permission to go here and here. And these are areas of motor cortex doing speech, as well as what's called hand knob that does hand motions, as Matt was saying. Over time, we can go into these areas like visual cortex, auditory, executive function, and it opens up completely new markets. And this is why what Elon talks about trying to restore vision for the blindness or restore people that are deaf, that's what he's talking about. Eventually, we're going to actually be able to take devices and go into multiple places at one time. And that's where the matrix comes in. Because if you think about the matrix, whether going into the spinal cord or the brain, if I'm actually inputting and outputting to all of your senses at one time, I can essentially recreate your reality. And the whole point of the Matrix movies, when you got to the very end of the trilogy, was if humans are able to create the Matrix, how do we already know we're not in one? So anyways, that's further out from actual addressable markets, but this is why BCI as a platform is so exciting.
From my standpoint, the thing that makes BCI very exciting is also that there are so many places where the gap between where we are now and what's happening in science fiction has some big gaps and some big questions. But in brain-computer interfaces, there are things that we can do right now for people. We can meet needs of people today where the markets are actually large enough to sustain a big company. And we can see a pathway to get to some of the science fiction-y, cool stuff just based on markets that we know exist. So for instance, we're looking at all of these different brain areas. Some of the areas are involved in executive function, attention, mood, cognition. Now, no one's going to sign up today and say, like, just throw a bunch of electrodes in my prefrontal cortex and let's see what we can do. But the way that it will happen is that there will be people who get motor prosthetics that can improve the function of their motor prosthetic by also getting a device in one of the executive control areas so that the motor prosthetic knows what sequence someone's going to do before they even try to do it, and that can help predict the movement of the robotic arm. Now, some of those same people who have devices in these executive functioning areas can be enrolled in secondary trials. They can volunteer to do things, math problems while we record from the BCI, or some people are going to have comorbidities, things like attention deficit disorder or mood disorders. And so even just with the first group of patients, we can start collecting data that can help us formulate hypotheses about the next market that we're going to go into. And so you can see there's this flywheel that builds up that at early clinical adoption builds better frontier models that allows for more clinical applications, more data, to the point where eventually we have a much more complete understanding of these brain areas.
Matt, I just wanted you also, so that you guys understand the underlying technology and how it works. Go ahead, question two.
Maybe someone gets drove, right? So if they lay down for a long time and he cannot speak some words, so you can use your
That is exactly the beachhead market, what we're going to be going after. Okay. Whether it's via ALS or severe dysarthria stemming from ischemic stroke, that is exactly the application that we're looking for. But I'll let Matt explain. This right here is the actual flow of how the technology really works.
Yeah. So we have the advantage of 20 years of translational neuroscience research that's happened at places like Stanford, University of California, San Francisco, University of California, Davis, a lot of the work, and Mass General Hospital in Boston, where people have received brain-computer interface devices that record from individual neurons. They try to move or try to do some kind of task, and that attempt can be inferred and produce an action on a computer. So in our first clinical trial, what that means is that we have a device that's sitting in the area of the motor cortex that would normally direct the mouth and the tongue and the larynx to form the sounds of speech. We capture these neuron signals, and through essentially a rehabilitation exercise, we tell the participant, try to do this, try to say that, try to say this. They attempt a number of times, and after enough attempts, we can build a decoding model to attempt what they were trying to say just based on the neural signals that we measured. And then we can have essentially a guess at all of the motor output they were trying to make, and then all of the sounds they were trying to make, and we can string those sounds together into sentences and make speech. Now, what's great is that we're currently drafting behind trillions of dollars of investment into edge compute and AI that make all of the downstream activities get better without us even trying. So even in just, we founded the company 10 years ago. Just in the last 10 years, the advances in language models are such that if we infer a sentence that the participant was trying to say, we can now infill errors with much higher fidelity than we could have 10 years ago, which means you can run the system faster, incur errors, and use the large language models to overcome those errors. 10 years ago, the devices that you would have used to run our models would have been beefy, servers and racks. Today, they're small NVIDIA systems that can sit on a wheelchair. And that's only going to get better and better to the point where these models are going to run on phones and watches when they go to market.
Okay, so this is a really important slide for everybody to understand and why data rates matter. Right now, today, this is where we're sitting. This is similar to the internet in the 1990s when we were using dial-up. Now, back in the 1990s, we could use the internet, right? We could do things, we could talk to people, we could even download music, actually, in the 1990s. But what did we do about the internet? We made it faster and faster and faster. And as the internet got faster and faster, we started to derive new applications from it. Everything from companies like Netflix were born. Now we can do edge compute. We can run enterprise workflows on the internet. We never used to do that. The same thing with BCI is happening right now. Starting back in the late 1980s with the first BCI devices, very slow, essentially operating in 1 to 2 bits per second, which is the equivalent data rate of being able to click a button. And now we've moved up into where Neuralink is today, replicating trials that we did back in the 90s and 2000s, operating about 10 bits per second, which is similar to cursor control. And so you see Neuralink's patients doing demos playing video games. That's why, because what they're basically implying from these things is push up, push down, pull a trigger, right, left. Those are the motions. As you move up in data rates, which again is a function of our electrode count and density as well as where we're going in the neural networks, we can start to do a lot more. So restoring speech, precision robotic control, and the sky's the limit really on the types of applications we can do. So Matt, please.
Yeah, so right now, our device, we've benchmarked it. Last year, we published a paper showing that we can support data rates of 200 bits per second. That's 20 times higher data rate than Neuralink has ever shown. But also, to be fair, it's more than we need for speech, but it's not as much that we need for a lot of applications. And, 200 bits per second, that's the data rate of modems in the late 80s. And so what's really core is not only that we're delivering this technology, but also that we have a roadmap for continuing to make it better in the way that Intel and NVIDIA and Qualcomm and TSMC have always continuously pushed forward their capabilities. We see that the future of brain-computer interfaces will follow more of a semiconductor model. Every approximately 3 years, the amount of information that you can push through a brain-computer interface will double, and that will have profound effects on what you can do with the technology. And it's going to be the companies that have the capability to continue reinventing themselves and continue pushing the technology forward that ultimately open up this space for all of the exciting things that we know it's possible.
Okay. I think because it's time, we're going to open up questions from offline audience and also online audience.
Can I ask a question?
Yeah. Sure.
So this system have to
whether the individual have to train by themselves or after your training you can apply to everybody?
That's a great question. So here's what we can say from data. As more people use a system, you can build models that make it easier for the next person to learn that system. One of the greatest examples has been there's a wristband that was made by a startup based out of New York called Control Labs. And I tried their wristband in 2017. It measures muscle activity from the forearm. So it's not exactly a BCI, lower fidelity, but when they were demoing it just prior to being acquired by Meta, it was kind of finicky, to be honest. The engineers who worked with it every day and that had trained it on their arm, they would get up and they would type and do really cool shit and people would be really impressed. And then you'd do a demo and it would be underwhelming. Now Meta had about 6,000 people use an improved version of that wristband. And what they found is by the time they got to 6,000 people, they had seen enough variability within people so that if a new person comes up and slaps it on their wrist, it immediately could subtype them, know a little bit about, implicitly the model knew about their physiology, and they could just use the model immediately. So I used it again just a few weeks ago. One of my friends works at Meta, and the control now for me, just putting it on, it was instantly workable. And so that's what will happen in BCI too. Now, I think actually the training curves are more favorable for BCI because there's more data and there's more signal. But that's what we've learned from these kinds of models.
I think that's a really good question, though, because also when you try to think about sustainable moats for businesses, we already know we're going away from software as being the sustainable moat. So your question on whether we can essentially build generalized decoders for humans. Every human we're obviously creating a custom decoder for at the moment, but as you make more and more of those, they start to look alike. Ours will start to look like Neuralinks. They'll start to look like Synchrons. They'll all start to look alike. So where you really differentiate again on these businesses is in the hardware and the processes that go behind making that hardware.
Yeah. Actually, if you go back to that slide where you have the matrix multiply, this is like when we think about what builds momentum in this space. So I just told you, I mean, I see this field evolving like a semiconductor company, and I see the market evolving like the internet. And so this data rate piece is essential. Whoever has the best data rate is going to be the NVIDIA of neurotech. But the other thing that's really important that gets exactly to your question is these frontier models can be a huge leg up and a moat in their own sense, but they require adoption. And not only do these models make performance for the people who are using it better, but they also give the hardware developers a leg up in understanding where the ball is going and what needs to be incorporated into the next version of the system. Everyone in tech knows feedback is critical. We think this is another area where we have an advantage over Neuralink. So one of the things we haven't talked about as much is device durability. So Elon's vision for brain-computer interfaces is one of essentially planned obsolescence, disposable devices like cell phones that you keep for 2 years and then you get rid of them. I think that's the world that he lives. He always lives 50 years in the future, and maybe 50 years in the future, people are willing to get brain surgeries every 2 years. But we don't have as many resources as him, so we have to think about what people want now and where the market is now. And where it is right now is people are willing to get brain-computer interfaces if they need it, as a therapeutic intervention to make their lives better, but no one wants to have to go under the knife twice, in 2 years. And so we spent a lot of time building our devices that it'll last more than 10 years and be robust. And we think that what that means is that the clinical adoption for our device is going to be much higher than the clinical adoption of the Neuralink device over the next 20 years. And what does that mean? That means that not only will we have that revenue, which will be essential for building a sustainable company, but that we'll have more data from more brain areas, which means that we'll be better able to build models and better able to inform the success of our next generation devices. And so in some weird way, by optimizing for the situation as it exists today, we actually think that we will still be able to ultimately succeed better in the future because we'll have more data supporting our development.